All right, as I was saying, it's much easier to observe these meteors at after midnight, between midnight and sunrise, and the reason for that is, um, yeah, and I just mentioned this, but it's like when you're walking through the rain, right? The front of you will get a little more wet than than the back of you, right? Because, or I think like if you're running through the rain, right? You're running into the rain, so that side of you is going to get a little wetter. Um, it's that's the basic idea. All right. All right. Most meteors are too small to reach Earth's surface by far. I mean, the vast majority of them burn up in the Earth's atmosphere and completely vaporize. However, there are some that do reach the ground. They're called meteorites. All right. So we're gonna classify those in just a second. All right. So comets and asteroids are the primary source of meteors. Right. So all this debris that's out there in space mostly comes from comets and asteroids, but not all of it. Some of it actually comes uh, from the moon and even from Mars in some cases. Not as much certainly, but like if let's say some large object hits, some large object like a comet or an asteroid itself collides with the moon, and of course we know that's taken place over time because the moon is just littered with these craters, right? And so is Mars to some extent. Um, but if let's take the moon, which is much closer, when something hits the moon and the impact is strong enough, it can throw up debris that will easily leave the moon, right? Because the escape velocity for the moon is very small, and the little pieces of the moon can rain down upon Earth. And this actually the same thing has happened with Mars, right? There are small chunks of rock that we've discovered, especially in Antarctic, because it's easier to find this rock on top of some ice, for example. Um, at any rate, if and then we analyze it, and it has the exact same chemical composition as rocks on Mars. And so the conclusion is, some of the material has actually come from Mars, due to some larger impact long ago, with some object like an asteroid or a comet hitting Mars and throwing debris out into space, and eventually some of that debris can fall onto the Earth. You know, that just statistically, there's a chance of that. I mean, it doesn't happen that much, but it does happen. All right, so now what we're going to do is we're going to classify these. So there's three main types of meteorites. Remember, meteorites are when these meteors strike the Earth and they're large enough to actually survive the atmosphere. That's called a meteorite. And so the three types are iron, stony, and then stony iron. All right. So I mean, it's pretty, it's pretty self-explanatory. But let me just go into this for a little bit. So the stony meteorites are made mostly of silicates, right? So silicate is silicon and oxygen bonded together. That like the average rock that you pick up on the ground is a silicate compound. All right. The rocks that you find that are a little heavier, they seem to have a greater density. Like that they're heavy for their size. Those are generally iron. They have some kind of. I mean, it doesn't have to be iron. It's more likely to be iron than anything else. But there's more metals in these iron. They collectively call them iron, but there could be aluminum in there. There could be, other metals. That, they're just collectively called iron meteorites. And then, of course, the ones which are there's mixtures of iron and stony. So there's silicate material and there's metals in them. All right. So these are called chondrules. These are like these little pebble-looking things that are in some of these meteorites. There's some of them that are called carbonaceous chondrites. They can have organic material in them, and the organic material is we've even found some that will actually have amino acids. Amino acids are the building blocks of protein, and so what that tells us is, the amino acids certainly have been around since the beginning of the solar system. Like amino acids can form out there in space, and that was an important discovery. Using these meteorites, the fact that there can be amino acids within the rock, that was a pretty major thing. There's also these sorry, it's hard to say. Achondrites. So these they lack these chondrules, and these are actually really hard to distinguish between just regular rocks on the Earth and they look basically just like regular rocks on the Earth. The one way that we can identify them as coming from space is when we find them in places like in the middle of the desert, right? So you find this chunk of rock where there's absolutely nothing but sand around, or you find this larger rock in the middle of like the Antarctic, right? So on top of the ice somewhere, where you don't find any other rock. Then it's very, very likely that it came from space. This is what the stony iron meteorites look like. It's kind of just a mixture of the two of them. All right. So most stony meteorites include small rounded chunks of rock and flakes of iron. And they're called chondrules. All right, chondrules. These meteorites are chondritic meteorites. All right. So the ones, some of the chondritic, the chondrules are embedded in this carbon-rich material. This is what I was mentioning before. It kind of looks almost coal-like. It's not coal, but it looks like it. And so they're called carbonaceous chondrites. So these ones are the ones where we have found amino acids in some cases. The ones without any chondrules are, as I mentioned before, achondrites. All right, so. And they're very hard to distinguish between ordinary rocks. All right, chondrules appear to have rapidly melted and then cooled in the solar nebula. There's actually radioactive material in some of these. Like they're good. I mean, all sorts of different radioactive materials. Like, for example, uranium-238, potassium. 40, things like that. and anyway, there's enough of it that we can actually date some of this material, and there in some cases we find that these things are 4.5 billion years old, so that they formed when the solar system formed. So carbonaceous matter contains organic compounds, including, as I mentioned before, amino acids, the building blocks of proteins, right? So the raw materials of life can actually form in space. This was a huge insight into, this is part of the reason that we're looking for life out there, even within the solar system, right? In places like Enceladus and Europa, because if you can find amino acids in these little chunks of rock that's floating around within the solar system, maybe this is everywhere, well, not everywhere, but in different locations in the solar system that could be favorable for life. And so we keep looking, because we've only found, make sure everybody understands this, we've only found life up to this point on the planet Earth. And so, it would be wonderful if we could identify living things somewhere else. All right, so now what we're going to do is we're going to turn to the asteroids. Asteroids are small, generally very rocky. Of course, they orbit the sun. Most asteroids, as it says here, most are in the region called the asteroid belt. All right, so this is between the orbit of Mars and the orbit of Jupiter. All right, so that's the main asteroid belt. Right? And there's literally thousands upon thousands of these things. By the way, it's not enough. Like, if you added up all the mass of all these thousands of asteroids, it's not enough for there to be a missing planet. A lot of people, when we first started studying this, this thing called Bode's Law is just, it's not important. Okay, so don't get into this. But some people thought that there should be another planet between Mars and Jupiter. Between Mars and Jupiter. There is actually a really large object that originally was called an asteroid. So it was actually the first asteroid. Well, I say it's an asteroid. It's actually not classified as an asteroid anymore. It's called Ceres. So this is, I think it was discovered in like 1801 or something like that. So this it's really large. It's by far the largest member of the asteroid belt. But now it's actually classified as a minor planet. It's not big enough to actually be considered a planet, by the way. The combined mass of all the asteroids is probably less than 1/1000th the mass of Earth. All right, so just to give you a sense of how little mass is out there. And the other thing is, like, the movies give you a really bad picture of the asteroid belt. If you were on it, if you were somewhere near an asteroid, let's say, you could see an asteroid outside your spaceship, you would not be able to, okay, let me make sure that's quite clear, you would not be able to see the next asteroid over. All right, they're not clumped together. I mean, there are thousands of them, but there's a lot of space between Mars and Jupiter, so you don't really see like a whole bunch of them clumped together, right? This is just showing you, where these things are. Like I said, if you were on one of them, there's so much space out there, you're not going to actually just look and see another one. All right, so this is the main asteroid belt between Mars and Jupiter. Notice this is the orbit of Ceres. And notice this is another thing. Okay, so we we classify Ceres as a minor planet because there's still stuff in that orbit.